So, what were we talking about last time? We talked about the Taylor-Proudman theorem. Remember? So what does the Taylor-Proudman theorem tell us about the kinds of motion that occur in the ocean?
They're like curtains.
They're like curtains.
But in the direction of the spin.
The rotation axis, yeah. So there's like columns that are aligned with the rotation axis that move around. Instead of tipping, shearing out in the vertical, or spiraling as they go down. And then at the end, we started to talk about the Ekman transport, the Ekman spiral, and why did that allow, it is a spiraling pattern. Where does the spiraling bit come from? What did we neglect in the Taylor-Proudman theorem that we bring back? Yeah?
Friction.
Friction, exactly. So we're going to pick back up on exactly that story and think through the friction again, and then we're going to see some consequences of the Ekman transport, and we're going to look at some of the equations that govern the Ekman transport today. That's the plan. So remember, the key principle of the Ekman transport was the idea that we would have wind blowing, and that would be in balance with the Coriolis force. And so the motion would be in between. And that was because of the directionality of the Coriolis force being to the right of your motion. And so to balance that with the wind, the motion needs to be to the right of the wind as well, in this kind of little schematic. Okay, so it's a balance between the Coriolis force and friction. So wind, I'm including as friction. Let's think a little bit about what I mean by that. So if we have wind blowing on the surface of the ocean, say, the wind would actually put a stress condition, like a certain input of momentum per unit area per unit time at the surface. And then what does the water do underneath? How does that stress condition is actually, you would have something else. So if you have a wind stress, then your surface boundary condition would be something like du dz times the viscosity is equal to the stress over the density of water. That would be the surface boundary condition that comes with the viscous term. So that's the way, so this is the viscosity or the friction, this is the frictional part. So the way the wind comes into the problem is kind of through a viscous boundary condition on the surface of the ocean. So let's look at our equations of motion and remind ourselves what that all came about. We had all this stuff, and then we said, oh, friction. What does friction look like? It might look something like this. So it would be du dz squared times the viscosity is the action of friction. So that was what it would be in our equations of motion. But now look, how many derivatives in z are in this equation? This one has just one, right? If you're in the vertical direction, it would have a vertical gradient. This would have just one. There would be one hiding inside of here in w d by dz terms, so that would have just one vertical derivative. This friction term that replaces that actually has two vertical derivatives. And so just from our thinking about differential equations, if we raise the differential order, we're going to have to provide new boundary conditions. And that's this. So, every time you solve a differential equation, if it's got, d by dx equal of phi equals whatever constant, to solve that equation, you'd have to specify the value of phi at some place, and then this would tell you the slope of phi, right? That's a solution to that, that's a solution to that, that's a solution to that. What differs about these is the initial condition. This is just saying the slope, x, phi. So the slope would be provided by whatever c is, but I could choose different initial conditions. All three of those are a solution to this equation. So if you want to tell me a unique solution, you have to tell me that boundary condition. If I did another one, phi, I would need another condition somewhere else, because then I could have, like 2 different things. So that's true of ODEs, like this. This is a ordinary differential equation X. It's true of PDEs. So the point I'm trying to make about when we introduce friction, one of the things we get is another boundary condition. And that other boundary condition is actually how wind stress enters the problem. Wind stress isn't in any of these equations. It's just a surface boundary condition on the friction. Okay? So, all right. Okay, so if we take this equation and we say, so how big is this term? We talked about the Ekman scaling, which is the viscosity, whatever it is, over F naught times H squared, which is just how big this term is expected to be, versus this term. The same way we did with the Rossby number, which was what? What term versus what was a Rossby number? Yeah, this one versus this one. So when the Rossby number was big, this term was bigger than that one. When the Rossby number was small, this term was bigger than that one. So for the Ekman number, we're comparing the Coriolis term to the friction term. And then you work that, and you say this guy scales like viscosity times 1 over vertical scale squared times velocity, and this scales like F times velocity. So you take the ratio of this one divided by that one, and you get this number. It's dimensionless. And the bigger the viscosity gets, the bigger the Ekman number gets. So Ekman is essentially a measure of how viscous the flow is. And last time we closed on the idea that even if the viscosity is really small, there's always some tiny layer where it gets important again, because this is inversely scaling with H. Does that make sense to everybody? So this is actually the thing that's going to control how deep our viscous layer is. When this is order 1, it's going to mean from there up to the surface, viscosity is going to be important. So if I set this equal to 1, that tells me that basically my depth scale is going to be the square root of viscosity over F, approximately. Okay? So if we set this to 1, and then play all of our other games, small Rossby number, don't worry about the pressure gradient, the way we have done before for Taylor-Proudman, we get a balance that looks like this. So we have Coriolis balancing the shear in the ddz squared of U with the viscosity, Coriolis balancing ddz squared of U with the Ekman number in the dimensionless form. Okay. Take a look at this. What direction are these 2 terms pointing? Let's suppose the wind stress is going this way. And that's just so we can look at it. So suppose the wind stress is going this way. Is it obvious which direction the flow is going with that wind stress? Not really. The flow has got to be going somewhere, but notice that this is a cross product, so whatever direction this flow is going, this thing is actually in a different, it's perpendicular to that. So some direction we've got like the surface velocity, and then some other direction we've got d by z squared, the Coriolis force is in some direction, and then in some other direction, we've got that. Can I say anything about the relationship between those two? Do they have to be perpendicular or something, each other or something like that? Hard to go through all this. This thing, because there's a cross product, So cross product is perpendicular to both of its ingredients. So this is perpendicular to whatever the rotation axis is, the F direction, and it's perpendicular to the surface direction, surface flow. This thing doesn't have to be oriented, it can be oriented in all kinds of crazy ways, but we actually do know its direction has to be perpendicular to both the vertical and the surface flow in order to have this equation balanced, right? In the direction along the surface flow, this side of the equation is 0, so this side of the equation has to be 0 too. So we do actually know that these guys, so I didn't draw it right, we don't know what direction they're pointing, but they actually need to be perpendicular to each other. Okay, just because of what cross product means here. Okay, all right, that's all a bit about the momentum equation. All right, so let's think of physically, let's step away from the equations for a minute and think physically about what's happening. Okay, the wind is blowing, and that's setting a boundary condition on the surface, so it's injecting momentum. Yeah?
Sorry, looking at that diagram, so is that both F and U are perpendicular to the second derivative, or is it the cross product is, I thought the cross product was equal to viscosity?
Oh, sorry, you're absolutely right. This guy has to be in the same direction as this guy. Squared. Which means that if that's the direction of that, then UE has to be in some other direction, which is perpendicular. Yeah. Sorry. Better. I think I said it right, but I drew it wrong. But we're going to see a force diagram that makes a simpler story than that, and it's going to be consistent with these ideas. We're just setting in the idea of perpendicularity having to do with the cross product. Okay, so if the wind blows and wind is injecting momentum, there's a stress on the surface. How deep does that stress go? How deep does that momentum go? What are some possibilities?
Infinitely, but it tapers out to almost 0.
Yeah, so we're continuously injecting momentum with a stress. So either a thin layer keeps speeding up, going faster and faster and faster, or some process keeps taking that momentum and moving it downward. Does that make sense? So what does this balance tell you just because there's no partial derivatives with respect to time in it? What does that kind of imply that this is thing that's happening here? That's a steady state. So whatever's going on with the momentum, it's being taken away at the right rate. And what's taking it away is this viscous term is just moving it downward. So that's what's balancing the stress comes out to be that. So we could make it go very quickly in the vertical with a lot of mixing, or we could make it go very slowly, and then we would build larger gradients. Either way, right? So this guy has both. We could have a bigger derivatives, or we could have a bigger coefficient out front. Either of those, that's two ways that we could think of handling, we could have a bigger viscosity or a bigger gradient in order to match the stress condition. So water normally has a very small viscosity, order 1 times 10. Viscosity of water, and the molecular viscosity is 1 times 10 to the minus 6 meters squared per second. So really small. But if we actually go out into the real world and blow a wind on the surface of the ocean, it does not just stay laminar. What happens is the surface of the ocean starts getting mixed up. And so we pretend that turbulence can be treated like a larger viscosity, one that would rapidly mix up this stuff. And so we have an eddy viscosity, which is a concept. It's not actually a very good fit to the way that turbulence really works. That would be approximately something like 5 orders of magnitude bigger than that. Okay? So the important thing here is like when you go to your model and you want to say, how deep is my Ekman layer? You don't want to use the molecular viscosity. We're going to want to think about that in a different way. The model is actually implementing a parameterization of turbulence that acts in this Ekman theory like a much larger viscosity. Because the eddies, turbulent eddies, are much bigger than, and much more massive than the molecules, so they are more efficient at redistributing momentum by mixing it up. Okay? All right, so let's assume that whatever viscosity it is, whether it's molecular or eddy, we know what it is, and actually we have a little e, so let's pretend it's an eddy one, and let's pretend it's constant. Okay? Then we can just write out our Coriolis force equals the viscosity ddz of u, and this is writing out in two components, and it actually is also putting in a background flow. So if you were riding on top of a Taylor-Proudman column down at the depth, this would just give you the deviation from that deeper flow. And that flow is imagined not to vary in z, so it only appears on the left, not on the right. Is everybody on board with me how that works? Okay? All right. So if we have a stress condition at the surface that looks just like this, viscosity times du dz equals tau, we'd have the u component be balanced by the x component of the wind stress, and the v component be balanced by the y component of the wind stress. So whatever orientation the wind's in, we can match it up. And in the interior, when we go below the Ekman layer, we would just have our velocity match to whatever the interior flow was. So that's our boundary condition at the bottom. This is the boundary condition at the top. This is the boundary condition at the bottom. We need two boundary conditions because they're two z derivatives. Okay? You could go through the process of solving these differential equations with these boundary conditions. But I tell you, these are the solutions. We can do it the other way and just guess and check. We know that there are going to be there is only going to be one unique solution because we specified all the boundary conditions we need for that. It has two equations, a u equation, a v equation. They have one top boundary condition each, one bottom boundary condition each. They're second order ordinary differential equations, and they're closed. So we actually know everything in the system. So we expect to find one unique solution that gives us two components of velocity as a function of depth, which is what both of these are. Okay. There's an exponential decay out front. That's good because we know that when the depth goes way, way, way down, we want to go back to just the leading bit. That's okay. Everybody's on board with that. We check that boundary condition. What about at the surface? If we set z to 0, this goes to 1, this goes to 1, this goes to some crazy something that looks like rho naught fd square root of 2. This guy goes to tau x times cosine of minus pi over 4 minus tau y of sine of pi over 4. Then this guy goes tau x, tau y. It's a little bit crazy. This one is contributing part of this balance, the cosine of pi over 4 and the sine of pi over 4. And this guy is contributing part of this balance. Okay?
Where does the sine cosine?
It comes from a second order ordinary differential equation is an exponential. And this one, in fact, is a complex exponential. So there's a real part and an imaginary part of that exponential. And if you write them out in terms of cosines and sines, this is the one that matches. Does that make sense? So if I have an equation that's like u equals v squared dz of u, I could just say, suppose u equals u at the surface times e to the minus z over h. Right? And I guess I'm on h squared there. Which one's what I want? Yeah, that was right. So, do I want a minus sign or a plus sign? Doesn't matter. So this is a solution to that equation. But so too is, I could put an I in there and make it imaginary. And if I did that, I would pull down two I's. That one's not. But plus or minus is a solution to that equation, right? Because I take two derivatives, whatever the sign is that comes down, it cancels out. Does that make sense? In this setting, it's more complicated because I have the V on this side and the U on this side and then the U on this side and the V on this side. So if I got it just to the U equation, it would look more like this. If I eliminated all the V's, it would be like a fourth order equation. Because if I take the U here and plug it into there, I'd have four derivatives. And so it's not just plus and minus that would be solution classes. It would be plus and minus and plus and minus I. And they would all be solutions to this equation. So you go through that algebra, you figure out which ones are which, and that's where the cosines times another exponential come in when you match to these boundary conditions. Because you have an e to the plus I, e to the minus I, an e to the plus, and an e to the minus, and then you match the boundary conditions and everything settles out to that. Okay? Okay, so this results in the Ekman spiral. So let's look at what that looks like. So at the surface, if you go in and plug in what all the pi over 4s are, it's actually not in the direction of the wind. It's 45 degrees to the right of the wind. And then it spirals around and around and around as it goes down to here. So if that's the direction of the surface, what direction is the Coriolis force on that surface flow? If the wind stress is this way, and the velocity is 45 degrees to the right, u surface, what direction is the Coriolis force on this? 90 degrees to the right of that, right? So it's not in balance. It can't balance that. It's in the wrong direction. So what's happening? There's friction because there's actually another layer below this layer that's a little bit like this, and it has a flow like that. So you're actually adding together the wind stress plus the stress on the layer below, and those two together are adding up to the Coriolis direction. So the reason why it spirals around is because you're adding drag at the surface, drag above, drag below together, and they're not in the same direction to get a Coriolis, balance of Coriolis force that's somewhere in the middle. Okay? Does that make plausible sense? So it spirals down and around. This is a beautiful solution. This is one of the first analytic solutions in oceanography, or I think it actually is the first analytic solution. The story is Nansen went out and froze himself in the ice. We talked about him already. And while he was there, he noticed that the flows didn't drift downwind. They drifted a little bit to the right of the wind. His observations were that they drifted about 20 degrees to the right of the wind. But he went home and told his student Ekman, and Ekman came back like a week later with this solution. It says 45 degrees to the right of the wind. It's not quantitatively accurate, but it is qualitatively accurate, and then since people have actually observed spiral-like patterns in the surface shear. But there's one critical assumption that this solution makes, which is not true in the real world, which is that this viscosity is not a constant. The ocean is roughly more turbulent at the top than it is deeper down. And so if this varies in the vertical, those details of like, is it 45 degrees off to the right, or is it 20 degrees to the right, is it 75 degrees to the right, change when the viscosity changes in the vertical. Okay, so the Ekman spiral is a nice toy version that relies on us having a constant eddy viscosity. we don't have a constant eddy viscosity, this solution isn't actually the right one. It's a more complicated solution that depends on the vertical profile of the viscosity as well as the vertical profile of the velocity. Super complicated, but we don't want to mess with that. We're actually going to do something simpler. Okay, but before we get there, we actually, this has F in it, so if we go to the southern hemisphere, we could just flip the sign of this and make negative F, which makes it spiral the other way. So in the southern hemisphere, it spirals around to the left instead of spiraling around to the right. But otherwise, it's the same balance. Same Coriolis balancing friction. Okay, so there is now a simpler force balance, which we said this one was complicated because we were balancing both on the flow above and the flow below to find an intermediate flow, and then we go a little deeper and that shifts around and around and around. What if we integrate over the whole force balance of the whole boundary layer, all the way top to the bottom of the Ekman layer? Then all of those little subtle changes in between would all sum up, and like the ones in the direction of the wind would cancel out to some degree with the ones opposing the wind, and the ones to the right of the wind would cancel out to some degree with the ones to the left of the wind. We can think about a force balance for that whole layer. We won't get all the interesting shears within the layer, but we'll get the average rate of motion of the whole layer. Does that make sense? So you can see that it's going to be complicated integrals to get these averages. There's e to the z's and cosines of z's multiplied by each other. And it's kind of like sitting around with your integral tables trying to figure out what all these work out to be. But there is a simpler way to think about it, which actually is a much more robust way to think about it in general, which is this little force diagram. The wind is applying a continual force in one direction, and at depth, we know that the friction is decaying as the magnitude of that velocity is decaying, so eventually we get deep enough that there's no more stress. So there's not a bottom drag on this Ekman layer, it's just experiencing wind force at the top, and that wind force, the only other force in the force balance is the Coriolis force. So if we just oppose those two, integrate it over the layer, then we come to a conclusion that the Ekman transport, that is the transport on average of the whole layer, has to be in between the wind and the Coriolis force. So what do I mean by Ekman transport? I mean that if we have the Ekman flow, which is a function of z, and we integrate from the surface down to the bottom of the Ekman layer, whatever that is, or you can go below. We can go to the bottom of the Ekman layer, or we can go to minus infinity, whatever we want. That would be the average times the depth of that layer. So the average, and this is a vector, and this is a vector. Okay? So it's the layer average flow. That we could have taken. Oh, should I just do it to get to that equation? Yeah, let's write that. Let's do it out. F cross equals viscosity. If I just integrate both sides of this equation in z, this one gives me F times that guy. Does that make sense, everybody? Sorry. I'm integrating over the whole layer. And what does this one give me? Fundamental theorem of calculus game. I'm integrating something, viscosity is constant. I'm integrating something that's a perfect derivative of the thing I'm integrating with respect to. What is that? Almost. not quite, it's not a change in velocity, I have two derivatives. It's the change in one derivative, evaluated at the surface, minus evaluated at the bottom. Okay? This one is down where the spiral has died off. So this one is just 0. This one goes away to nothing. What's this one? Feel free to look one line above it. That's the wind stress. So that equals tau over rho naught. So looking on this side, and this side, we have a balance. That one. So the integral of the velocity dz, which we have written as just the average velocity times the layer depth, but you could also just keep it this way, is equal to tau cross z over rho f. The cross z is a little crazy. It's because this one's got the f cross over here, and this one's got the tau over here. If you want to move the cross to the other side, you've got to do some checking around, but this is the right sign. Okay? Does everybody see where that comes from? So this is the integral. What's interesting about this? And where's the viscosity? It's not there, because here's the viscosity right here, but then I substitute for something that also depends the same way on the viscosity, so I just got the tau. So the magic thing about this formula is it doesn't matter whether the viscosity is some complicated function of z. This derivation still works. Okay? This force balance still works. So this one in the real world always happens. The Ekman spiral only happens under magic, kind of very steady conditions where that spiral could build up. This one actually holds even in strongly turbulent conditions with all kinds of crazy other processes going on. And it's basically just this force balance of the wind, Coriolis, flow in between. Okay? Constant momentum over the whole Ekman layer. This is not sensitive to the details of any viscosity. So we're saying all the same things in words that I've already said. Okay. Yeah.
You're talking about two different types of viscosity, the turbulent viscosity and molecular. When you're talking about the Ekman depth,
Mm-hmm.
we'll normally talk about the turbulent Ekman depth.
Yeah. So what we mean by the Ekman depth is we're going deep enough that this term vanishes. And essentially what that means is you go deep enough that the shear is vanishing, which is kind of in a real turbulent layer. It's just you go to both some depth below where the turbulence is really moving a lot of momentum. So if basically the turbulence is moving a lot, turbulence is moving a lot, turbulence is moving a lot, then there's a bottom to that, and then you drop off. So there's some complicated shear profile over a while, but eventually it settles down to the interior flow. That's what the Ekman depth it really is. It's the depth over which the momentum is being mixed by turbulence.
Would you see two spirals, like one in the sublayer?
Yeah. So if you had a complicated viscosity profile that was like a lot of mixing and then none and then more, you would have like a spiral for a little while, then it would stay steady, and then it would spiral around more at the bottom. So you could get complicated profiles like that. Or you could get one that was really, really well mixed in the vertical, so that basically it was like uniform flow in the top, and then it starts spiraling around only at the bottom where there were, I mean, you can get a lot of funky things like this, but this force balance still holds for all of them. Okay. Assuming that Coriolis equals friction balance is still the dominant balance. If we had some DDT, like if the wind was changing a lot in time, then this wouldn't hold because the DDT term would come in. Or if we had some pressure gradients at the surface, this wouldn't be the only show in town. There would be some pressure gradient forces. We'd have to think about what they balanced with. This is just the Ekman bit. So just that surface layer contribution adding on top of whatever else is going on below. Okay. This momentum balance is also true looking up. the atmosphere exerts a stress on the ocean, but the ocean is also exerting the same stress on the atmosphere, which means that the atmospheric boundary layer also has an Ekman transport. And this is the same integration. So this is the same integral looking up for the atmosphere. So the atmosphere should have an equal and opposite Ekman transport in terms of mass transport in the atmosphere, which is kind of a cool thing. Sometimes it's important in the atmosphere. All right. Okay, so we have these little schematics then from Colin. We have the spiral, which is a vision that depends on knowing the viscosity profile, or we just have the average motion of the whole layer, which doesn't depend on the details. Okay, so let's think about some practical applications. That's what the balance looks like. Let's think about some situations in the real world. And this is where your paper is really going to come. You're going to pick a situation in the real world or in the echo world and go measure everything. Go look at the wind stress curl, the offshore flow, the onshore flow, the cross-shore flow, the upwelling, the SST anomaly. All those things are all going to be hooked together. And that's where we want to build a story. Those equations that we already went through are enough to do the homework. The Ekman spiral question and the force balance, those are the only equations you need. You just have to figure out the orientation, sorting out the cross products to get those questions right. Okay? All right. So we've seen the Ekman spiral, which is sensitive today. We've seen the robust Ekman transport. What are the implications? Okay, we have this guy. And we have the southern hemisphere version, which is the mirror reflection. Okay. What if we go to the equator? And at the equator on the Earth, we normally have trade winds, which are blowing from the east to the west. And that has to do with atmospheric circulation stuff. What Ekman transport does a flow from the east to the west imply in the northern hemisphere? It should be going in the northern hemisphere. It should be going to the right of the wind, right? In order to have the Coriolis force that's opposing the winds. So it goes northward. In the southern hemisphere, it should be going to the left of the wind in order to have a Coriolis force that's going towards the east. So they diverge. What happens if the surface water goes away from the equator? Stuff is going to come up from below to fill it up. So there should be upwelling, bringing up cold water at the equator, and actually the picnic line will kind of bulge up to match. The sea surface height will have a little downward anomaly because it won't perfectly get replaced by this new inflowing water. There'll be a little pressure gradient residual. That's what the equator looks like everywhere in the world to leading order. The cold tongue that's part of the Pacific El Nino is cold because of this equatorial upwelling. There's a cold tongue in the Atlantic too. There's the Indian Ocean dipole and the Indian Ocean currents, which set up an equatorial upwelling zone in the Indian Ocean. That's what it is. And you guys now have the full, well, 3/4 of the dynamical understanding to understand why that's there. Okay? And the situation is that the Ekman transport was away from something that couldn't replace it with just more Ekman. What if we go near a coast? If the wind is blowing along the coast in the northern hemisphere, which way does the Ekman transport go? To the right of the wind, this way. So that's what these little arrows are saying. Which means that you have to have something come up from below to replace it. So you get coastal upwelling when you have an alongshore wind. If we did it in the southern hemisphere, the alongshore wind would be going the other way to drive it off. In both cases, this is an equatorward wind that is driving upwelling. A poleward wind would drive downwelling. It would push water onto the shore and would tend to have another one. And then there's a whole mess of other currents that result from this anomaly that we're going to get to understand as we understand geostrophy. But from the perspective of your paper, what might you go look at in the model to look for either an equatorial or a coastal upwelling?
You could look for nutrients.
You could look for nutrients. The Ekman model doesn't have nutrients, but if you had a model with nutrients, you would see nutrients being brought up from this deeper water. What about temperature? The deeper water is going to be colder. So if you see that it gets colder right as you approach the shore, it's probably upwelling. How do you check that it's upwelling? You look for vertical velocity right near shore, going up. That would be coming up to replace this water. Or you could look for horizontal offshore transport right at the surface. You could measure the Ekman layer depth by seeing how deep that offshore transport goes. You could check this equation by finding the component of the alongshore wind and seeing if it balances the depth integrated offshore transport. That would be a nice thing to check. If there were complicated currents from all these other stuff going on underneath, you could subtract them off, just like we did with the Ekman spiral first, and just look for the upper ocean, like upper 50 meters deviation from whatever the current is at 100 meters. So just take the mean current from like 50 meters to 150 meters, subtract whatever that value is off all the way up to the surface, and then just look at that little shear right near the surface. That should be close to Ekman balance. All of those pieces are Ekman. But then the interesting thing is that these are really important places because they bring nutrients, they lead to blooms, they have huge impacts on cloud cover, they have all of these feedbacks back into the climate system. So those places are special places with a lot of science written about them. You can go in the ECHO model and talk about what the upwelling results from and how it works and what it looks like and make maps. That's the essential idea. Okay, there's one really important one that we're going to dwell on a lot in the class, but on first viewing is a little bit subtle. Okay, if we're in the northern hemisphere and we have a change in the winds from place to place. So it's going this way over here and it's going that way over there. Which way does the Ekman transport go? The Ekman transport for this one goes which way? This way, to the right. Ekman transport this one, that way. So it collides somewhere in between those. If you have colliding Ekman transports, that means it's going to drive downwind. Not at the coast, not at the equator, just out in the middle of the ocean. This pattern in wind stresses will do that. If we reverse the sign and put this direction of wind next to this direction of wind, it's going to drive Ekman the other way, and it's going to drive upwell. So this is an open ocean subduction or upwelling driven by changes in the surface winds. Okay? Here's our little equation for mass transport in the boundary layer. This goes like the wind stress. If our water is incompressible, how do I get from mass transport to vertical velocity? This is a fun one. Okay. d by dx of u plus d by dy of v plus d by dw of z. Bah! That one's backwards. Equals 0. That's my, remember, nearly incompressible ocean has this. How do I find z instead of the z derivative? What can I do to get the w outside of itself? Integrate in z. So if I integrate this,
The surface z is just 0.
then I get, wow, look, d by dx of u plus d by dy of v integral equals, let's do it 2 steps, dz plus w at z equals 0 minus w at z equals minus h equals 0. And if this one is 0 because there's not water flowing out of the surface of the ocean up into the air, then this is the only one that's left. We can move to the other side, and we just have this guy equals w at z equals minus h. It's this. W equals minus divergence of the horizontal velocity. And since we're talking about the surface, we might just say, well, what's going to make that convergence is this process. So what if we just plug in for that the Ekman spiral velocity? And we do that, we plug in the divergence of, we actually know v dz, like that. We play games through the derivatives, and that is the predicted vertical velocity at the base of the Ekman layer. So it says the curl of the wind stress over F with a density to cancel the units of wind stress mass. Tau over F, the curl of that drives upwelling or downwelling. So, all right, is the curl of this positive or negative? Everybody know how to do the right-handed rule on curls. If you wrap your fingers around in the direction of the spiraling bit, the direction your thumb points is the direction of the curl. So this one is spiraling around that way. So the curl is downward, and we said it was northern hemisphere, so F is positive. So this guy is downward, down. We go over here. Now we spiral our fingers around. Our thumb points up. The curl is upward. F is positive. That's this way. We can go to the southern hemisphere. We get exactly the same curl of tau, but F switches sign. And so this wind pattern would lead to downwelling. This wind pattern would lead to upwelling. Cool? This kind of motion is the way that the winds make the ocean move. This is like the most fundamental, important thing about large-scale ocean circulation. Like if there's just one idea that's important about how the oceans move from this whole class, it's this. It seems a little subtle and a little bizarre, but you will see that we just keep building on this idea that you get convergence of the Ekman layers, pushing stuff down or lifting stuff up below, and that will make all the stuff in the interior do magic. And the magic is going to be a little complicated to think about. Okay, so we have coastal upwelling, we have equatorial upwelling, and then we have Ekman pumping and suction, which is not to do with the wind stress itself, but to do with the curl of the wind stress. Okay? And actually, the secret, you will find literature, depending on where you look, that talks about coastal upwelling. Is coastal upwelling because of this? Or is coastal upwelling because of this? There are a lot of people who write a lot of papers about this. It is my personal opinion that they are all wrong. Because if you integrate this equation right, you get this scenario. So the fact that this one depends on the wind stress and the other one depends on the curl is just the way you do the integral from the boundary layer out. So if you get the wall right and put that condition on what the flow looks like, those two are the same thing. But I guarantee that if you go and you want to do a coastal upwelling problem, there will be like 3 or 4 papers on whatever upwelling region you like where they say, is it the coastal upwelling or is it the Ekman pumping that's doing the upwelling in our region? They are just the same thing. But then they do the boundary conditions wrong on this integral and it all goes haywire. Okay? So I will warn you on that. Okay. So can we see this in the real world? Yeah, we can. So these are satellite in movies from Modus, which detects chlorophyll by ocean color, and detects sea surface temperature, also by ocean color, by ocean infrared color, if you like. Look at all these hot zones along the equator and along the eastern boundaries. Those are all upwelling places where the wind is blowing equatorward along the coasts, or the wind is blowing trade wind while westward along the equator. So that deeper water is being brought up and it's blooming. And so we see it in chlorophyll. There's some seasonality. It's not clear whether the seasonality is because of the critters liking different seasons or the upwelling liking different seasons. We'd have to look at the wind map to see that. But that's exactly the kind of thing you could do for your project. There's also a broader productive zone down here and a broader productive zone through the subpolar gyres up there. That's because of the wind curl. Those are regions where there is a broad upwelling throughout the entire gyre that's bringing up water. It's not as intense, so the nutrient concentrations are not as high, but there is a resupply of nutrients to the surface because of that curl equaling upward. Curl over of tau over F. SST, you see here's the cold tongue in the Pacific. This is kind of hard to see. There's the cold tongue. Some seasons show it nicely. So it has a coastal upwelling part and it has an equatorial part. There's a similar one in the Atlantic. It's not as strong over here in the Benguela current, the upwelling zone over there. And then there's similar features over here. The wind stress curl reverses direction seasonally in the Arabian Sea due to the monsoon. And so some seasons it's upwelling and some seasons it's downwelling. This part of the world is very interesting for the wind forcing patterns. So there's lots of interesting stuff to think about there. But again, you see these cold regions, they're not exactly the same as just upwelling driven. It's also colder near the poles. So it's not clear which one it is, the way that it is clear that the upwelling drives the productivity. But an aspect of this is that cold water is actually being brought up to the surface. Okay? So it really matters. Yeah.
Is there a scale for the wind for it to be important enough to drive the Ekman?
We believe that the Ekman transport is not limited by scale. What happens is you get small enough and the Rossby number goes up, and so the Coriolis part isn't that important, and so smaller winds don't drive an adjustment. So either time variable winds or small scale winds produce currents that the Rossby number is too high for the Ekman transport really to work. But you can actually generalize the Ekman transport even into moderately high Rossby number through using a nonlinear Ekman balance, which is like a submesoscale thing. So you can start to think about all kinds of stuff here's an even more complicated scenario of winds going onshore and offshore. There's an eastern boundary. So what's that wind pattern going to do? Is that going to converge the surface or is it going to diverge the surface flow? Converge it, push it down. So if you look at this density class, it's going to get pushed down out of the surface and then it's going to spread out somewhere. So this is called a subduction zone. And so all through this wind pattern, the surface water is getting pushed down and imprinted below the Ekman layer into the deeper water. Over here, there's something called the shadow zone, which is an isolated region that doesn't get contacted by that subduction. And so this water is not refreshed with surface water. What are some of the things that would be characteristic of surface waters in terms of like other chemicals it might have in it besides water? It's been at the surface a long time. Maybe say all the phytoplankton have eaten up all the nutrients. There are not any nutrients left. So it might be nutrient poor. That's one thing.
It'd still have oxygen if it was near the surface.
It'll have a lot of oxygen from oxygen exchange. It'll be basically equilibrating oxygen, equilibrating carbon dioxide. So this water that's coming down will have essentially atmospheric level concentrations of carbon dioxide, oxygen, CFCs, methane, whatever. This water has been down there a long, long time and isn't getting refreshed. So if there are creatures down there eating up oxygen, like fish or other heterotrophs, other kinds of things that consume oxygen and not rather than producing it, this oxygen would slowly decrease as you went away from the surface, but this is not refreshed, so it would be very, very low in oxygen. In fact, every ocean in the world has something called the oxygen minimum zone, and it is precisely defined by the boundaries of where the subduction does not reach. There's a low oxygen on the eastern side of all the ocean basins that just because it's not getting refreshed by this downward surface water converging and going down. Okay, let's go to the other one. Okay, so quick break. So we talked about the Ekman transfer, we talked about the Ekman spiral, we talked about the convergences. Let's think about this in the bigger picture, and then we're going to come back to how this is going to affect the deeper circulation a little, following on that idea of subduction. Okay? So, remember our game here is we've got these complicated equations of motion, particularly this nonlinear term. This is kind of horrible to think about. But we can go through and guess how big the different terms are in different balances, and then isolate the biggest term balance. So hydrostatic balance told us what? Yeah, so the pressure increases with depth according to gravity plus the Coriolis force, centrifugal force. So whatever is that gravity-like thing that's pulling stuff down, the weight of the stuff above you is related to the pressure. The Taylor-Proudman theorem involves three different terms being big, but essentially we neglected the variations in density, we neglected friction, we neglected this, and that told us that the motion ended up being columnar. It went around like that. So the Ekman number was small for Taylor-Proudman because friction was small. The advective Rossby number was small because the advection term was small. The temporal Rossby number was small because the DET term was small. Okay? The Ekman layer, this one balances this one. The Ekman number was how big? Or 1, because that's the balance between those two. The Rossby number was small. The temporal Rossby number was small because we neglected this term and this term relate to that. We haven't totally left out the idea that there could be some pressure gradients lurking underneath this, but we're going to just put a little surface layer on top of whatever's else going on. So if there's a deep Taylor column, we could put an Ekman layer just on top of it. I'm going to make that more formal in a minute. Inertial oscillations, were the Coriolis force balancing the time derivative. So in this case, it was inviscid, so the Ekman number was small. The advective Rossby number was small, but the temporal Rossby number was order 1. Okay? So we've seen a lot of different classes of balances. So our procedure is we can estimate the different scales of the motion by just looking in the real world. How big is the time scale, the length scale, the velocity scale, the depth scale? Scale of terms in the equation. See which ones pop out, which ones are the big ones. And then we pay attention to the kinds of balances that might make that up. And we've come up with this whole zoo of different dimensionless numbers. And so it doesn't matter what units we measure them in, they're the same number, they're dimensionless. There's the Reynolds one, which talks about momentum versus viscosity. So you might have heard that one. We actually haven't talked about that one, but that's a different way of measuring the Ekman number. There's a Rossby number, temporal Rossby number. There are lots more. Okay. Well, I have repeated those equations. Anyway, okay, so we have this Ekman balance. We have this idea of molecular viscosity. We have the scaling momentum. This is just repeating what we just said. Equatorial upwelling. No, wait, what happened to the one? There's one more slide I wanted to show. There you go. Made it. It's all pretty. It had lots of colors. All right. Well, it'll come along. Let's talk a little bit more about what all this upwelling and downwelling does in the real world. Okay. Here's the whole world. These arrows are a very rough approximation of the way that the typical winds go. So you can look at that for a second. So here are the trade winds. Here are the westerlies. Here are the westerlies. These are sometimes called the roaring 40s because the westerlies are really big and 40 degrees north and south. And then there's all kinds of interesting stuff. But let's be even cruder than this map. And let's just say that's the way the winds go. So we've got the roaring 40s, which is 40 degrees north and south coming from the west. And we've got the trade winds coming from the east. We're going to forget about all these interesting north-south pieces for now. Which way does the Ekman transport go? For this one. South. For this one. North. For this one. North on the north side, south on the south side. So you get this. So in this whole band, Ekman transport is converging. If you calculated the curl of the wind stress over this whole band, it would give you a downward Ekman velocity at the base of the mixed layer, at the base of the Ekman layer. This is a convergence zone all through these subtropics. So between the tropics and the westerlies is the subtropics. That's this area. This is where the descending, let's see, this is the descending branch of the Hadley cell and the storm tracks out here. So it's kind of like halfway in the Hadley cell, halfway underneath the storm tracks. But the wind stress curl here is toward convergence. It's also toward convergence in the northern hemisphere. It's also towards convergence in the Indian Ocean, and it's toward convergence even on that side, even though there's not like a real North Indian Ocean. There's just the Arabian Sea and the Bay of Bengal. Down here, see, the wind continues in that same direction, so it actually is still going that way, but it's going that way less and less. So there's actually a diverging winds all over the Southern Ocean. So there's Ekman upwelling. There's diverging here. There's diverging here. Ekman downwelling. Ekman upwelling. So upwelling in the subpolar regions, upwelling. Convergence, downwelling in the subtropical regions, divergence, upwelling in the subpolar regions. That's the basic picture of how the winds drive Ekman transport. And so we saw these little coastal signatures, but we can actually do more than that. We can start to look ahead for what we're going to be writing the next paper about by thinking about how convergence would affect the pressure field. So remember we had this little game where we talked about the hydrostatic balance is the vertical momentum, it's that balance. And it's basically the weight above you per unit area gives you the pressure. So we have a tall stack of pillows. How much weight does that have versus a short stack of bricks? Kind of the same, right? So we might have medium pressure underneath a short dense thing or a tall not dense thing. Okay? If we had the same height of something that was high density and something that was low density, we would have higher pressure underneath, lower pressure underneath, because they're starting at zero at the same point. The weight is accumulating faster over here than it is over here. Everybody on board with me for that? Okay. So if we think about the surface of the ocean going up and down at a relatively constant density, we would expect to have low pressure underneath the low bits of water and high pressure underneath the high bits of water. That's because of the height of the stack, not because of the changes in density. Okay? Already said that one. But we know that the ocean actually has a picnic line, so the density is lower, and then suddenly it goes up a lot, and then it's a lot higher below. So that's the way that it works. So we can change the sea surface height, and we could change the pressure field in the horizontal, or we could push the picnic line up and down. And if we push the picnic line up and down, it's like making bricks into pillows. Yeah.
Sorry, this is my first experience. What's the picnic line?
Sorry, the picnic line we talked briefly about, it's because there's warmer water at the surface and fresher water at the surface, there's less dense water at the surface, and then when you go deeper, it gets more dense. So the denser water is below the surface water, which is less dense. And it turns out that the profile looks something like this, where the density is low, and then the picnic line is the part where it rapidly goes from low to high, and then it's relatively uniform as we go down. We talked about this on the potential temperature, potential density days. Okay, so let's contemplate this particular setting. If we had a bulge of sea surface height, this light layer would start higher up in the middle than it would be on the sides. Okay? So right at this depth, where's the pressure going to be the highest? Center, because these all have the same density, they're all pillows, but this stack of pillows starts higher up, so it's taller. So there's more weight of pillows on top of you here. What about when I go here? I have a tall stack of pillows and a little bit of bricks versus a short stack of pillows and a taller stack of bricks. Same over here. That is going below the base of the picnic line. The picnic line is inversely bowed away from the sea surface height. It's hard to do this quantitatively, I will agree with that, but does the pressure difference from here to here, is that bigger or smaller than the pressure difference from here to here? This is going to be a big difference, but the taller bricks here are where the pillows were taller here. So it's going to be a compensating effect. So once you go through the picnic line, you actually expect the pressure differences to go back down. So they are big, and then they get smaller. Does that sort of make sense to everybody? We're going to keep talking about this a lot. Just want to start these gears turning. Okay. So if we go back to this convergence pattern, what do you think is going to happen? If we push stuff into the surface, what's going to happen to the surface? It's going to go up. You'll probably have a high surface here. But if you're pushing stuff in the surface layer and above the picnic line, what's going to happen to the picnic line? It's going to go down. So we expect this kind of thing to happen in all of the subtropics. We expect the surface to go up. We expect the picnic line to go down, just because of the convergence of that surface water. Okay? It's actually a more complicated story than that, but that's not totally dissimilar from what happens in the real world. This is a map of pressure, and not our version of the echo model, but a different version of the echo model, at 5 meters depth. So this is 5 decibars at 5 meters. So this would be the pressure you just expect at 5 meters average depth. But in some places, there's more water above you, like 7 meters of water. And in some places, there's only like 3 meters of water above you, because the surface of the ocean is going up and down from place to place by about 4 meters. Where are the places where the sea surface height is high? subtropics where the Ekman transport is convergent. Where are the places where the sea surface height is low? The Southern Ocean and the subpolar gyres, where the sea surface is diverging. So basically, we're seeing on a large scale the same kind of converging, diverging dynamics that happen up against in the equatorial zone or the coastal zone, but we're seeing it on a huge scale. And what we're going to learn starting next time is we're going to learn how these pressure gradients that result from this drive currents. And when the pressure gradients drive currents, these things are not going to be just a stable pile of water, they're actually going to be spinning piles of water. And the spinning piles of water is going to tell us about essentially all of the rest of the large-scale currents in the world that we haven't talked about so far. So we have inertial oscillations, we have Ekman transport, we have Taylor-Proudman, and these spinning ones are actually going to be close to Taylor-Proudman. The deep ones are anyway. But they're going to spin because of these pressure gradients. In order to keep the pressure gradients in balance with the Coriolis force, they have to be spinning. Does that make sense? So the Ekman transport is the way that these pressure gradients get established, and then those pressure gradients are the key to what makes the oceans, sets the oceans in motion, be it below the surface layer. Okay? All right, questions? Oh, do I have the deeper one? Oh yeah, I do. We go deeper in the model, down to 1,533 meters. There's almost no pressure gradients because the Pictocline went the opposite way of the surface and canceled it out. Only the Southern Ocean still has pressure gradients down at that depth. So that means whatever is causing these pressure gradients, it's a surface phenomena, and somewhere between 5 meters and 1,500 meters, the density structure is compensating. We're going to think about what that means and how deep we expect those currents to be because of that. Yeah.
So when you're talking about the Pictocline getting larger, is that, do you think of that as the convergence and divergence zones being not as effective? Because you would think that when you have convergence and that those cause a downwelling region because of the compressibility, but in fact it's extending instead of just continuing what you would think.
Yeah, so if there weren't any density in the ocean, you actually would just have convergences and divergences in the surface boundary layer and the bottom boundary layer. And so essentially what happens when you had a convergence, you would pile up a little bit of water, there'd be a vertical velocity, and then it would spill out into the bottom boundary layer, and that would make things move around. When you do have the density in the way, it goes, when you converge, it goes down and goes up, so it traps that flow in just the upper part of the ocean. It doesn't make it all the way down to the bottom boundary layer. So in that sense, it's not as effective. But it turns out that the currents that get forced are more intense when they're only in the surface part. So it's not exactly less intense always, because the resulting flow, because of the pressure gradients, is actually more intense when you keep it only in the upper ocean.
That's because it's not true, incompressibility is not true in the entire ocean depth. It's because you have stratification, then that's what causes the expanding.
It's not quite incompressibility. It's like the pressure gradients don't like to rub on the bottom, essentially. If they do, they get damped out. So that motion gets trapped in between the Pictocline and the surface more than it goes all the way down. That's kind of a anthropomorphic sense. But it's all still incompressible flow. And it's all horizontally incompressible outside of the Ekman layer, which we're going to see next time. So those are all characteristics that are leading up to this, but there are a lot of different threads to get to the way the large scale flows. And by the end, we'll have kind of 3 different ways of thinking about this. So for the paper, number 2, you're going to choose an Ekman upwelling region, and you're going to describe it, much like we did with the statistics, except now you have some inkling of why there are motions. You will be able to look at the wind stress, and the wind stress will be a cause for upwelling. And upwelling will drive currents, and you'll be able to figure out which direction they should go, and you'll be able to figure out whether they should be converging or diverging, and you'll be able to say, that should make the picnic line go up, or that should make the picnic line go down, or that should make the surface waters cold, or that should make the surface waters warm. And then you will look for those consequences. So it'll be a little bit like a budget exercise, and that you're thinking about like flows into and out of a region, but we now know we have an explanation for the flows now. The flows are there because of the wind. And so that's going to put a little extra cause into the story. Sorry.